it will be time to chat a little bit after the end of the seminar. So our speaker today is Alexander Lazar. He is a postdoc currently at KTH, Sweden. And he's working mainly in algebraic and topological combinatorics. And today he will talk about partition and Cohen-Macaulay extenders. So Alexander, please.
Thanks for having me, Russ, Andres, and Stefko. It's great to be here virtually. I wish I could be here in person, but maybe sometime soon when things have calmed down a little bit. So today I want to talk about some joint work that I did with Joseph Doolittle, who is most recently at Freie Universit Berlin, but is moving to Graz in Austria, and Bennet Goeckner, who's currently at the University of Washington in Seattle. And as Stefko said, I'm talking about partition and Cohen-Macaulay extenders. And if you don't know any of those words other than "and," I will be explaining what everything is throughout the talk. If I can make the slides advance. So the primary object of study in this kind of research is a simplicial complex. So here we're going to mostly treat simplicial complexes as abstract combinatorial objects as opposed to topological spaces, but they are in many ways those perspectives are essentially equivalent. So we're going to freely move back and forth between them. So for today, a finite simplicial complex, and usually this is denoted delta because delta looks like a triangle, is a finite collection of finite sets, and these sets are called faces. And the requirement that we have for these things is they're closed under taking subsets. So if we have a face sigma of delta and tau is a subset of sigma, then tau is also in delta. We can talk, as I said, there's a way in which these things are topological in nature. So we have a meaningful notion of dimension. So the dimension of a face is just the size of the face minus 1. And we take the dimension of the complex to be the largest dimension of a face. And on the next slide, there'll be an illustration of what this is if you're not super familiar with this branch of combinatorics. And we have a little more structure on this collection of faces. We can organize them as a partially ordered set. Because we have this notion of containment, they're going to be, in general, partially ordered by containment. And we denote this partially ordered set by fancy f of delta. This is called the face poset. And some of these faces have special names. A maximal face with respect to inclusion is called a facet. And we call the complex pure if all its facets have the same size. So here's an example of a simplicial complex. I'm not going to go through and check that this satisfies the notion of being closed under containment, but if you want, you can check it yourself. So here is a geometric representation of this complex. So what we do is a set of size k. We think of this as like the convex hull of k points in general position in Euclidean space. And then, this is in 2 large dimensions, so we can push things down a little bit. So for example, a collection of 3 points, if they're in general position and you take their convex hull, you're going to get a triangle. And so the sets of size 3 are triangles. And in general, if I have a set of size k, I'm going to get a k minus 1 simplex. So if I had sets of size 4, these would be solid tetrahedra, and so on. And the correspondence here is just the set is the vertex set of the simplex that we would get if we took their convex hull. So the complex we're considering here is going to be sort of our running counterexample throughout the rest of this talk. It doesn't have a lot of properties that we would kind of like it to have, but it's sort of the smallest complex that doesn't have these properties. And so this is called the bow tie complex because it looks kind of like a bow tie. So on the right, we have its face poset. And so notice that we always take the empty set to be a face of the complex, unless the complex is itself empty, which is something that we want to allow for technical reasons. So over here, we see we can pass from this set system up top to a sort of topological or geometric object on the left to a poset on the right. And these perspectives are all going to be useful for understanding the combinatorics or topology of this object. So we're going to try and pass back and forth among them. And one last thing to note is that this set system representation is not really the most compact way of understanding these objects. So if I just tell you what the maximal faces are, so what the facets are, I know that I have to have all subsets of a facet. So really I can get away with just writing down what these facets are. And then so I'm going to, and that cuts down the amount of space I need to write things down. So in general, I'm going to use angle braces to indicate that the complex is generated by these facets. So it's the collection of all subsets of the things that are inside the angle braces. And by the way, if anybody has any questions about anything, please interrupt in the chat and I will attempt to answer. So this is just kind of the general setting that we're working in. Okay, so in general, we're going to fix our dimension when we're working with a complex. So we'll let delta be d-dimensional in this case, which means that its facets have size d+1. And in this particular sub-branch of combinatorics, there's going to be a lot of off by one errors because dimension is one smaller than the size, and this happens a lot. One sort of obvious invariant combinatorially of these objects is we can count the number of faces by dimension. And we'll let fi of delta be the number of I-dimensional faces of delta. And we can write these face numbers down in a vector, which is typically called the f vector. One thing to note is that for reasons that will become clear in a second, we always want to include this f-1. And you can think of this as the number of empty faces, the number of empty sets that are in your complex. So it's going to be 1 unless delta is itself the empty complex. And in general, so f0 is the number of vertices, f1 is the number of edges, and so on. Fd is the number of d-dimensional simplices. So the f vector has a nice, is sort of an easy invariant. A little more subtle is something called the h vector. So we notice that for a d-dimensional complex, the f vector has size d+2. The h vector is some other integer vector that also has size d+2. We start at h0 and we go to h d+1. And it's actually equivalent to the f vector. The way you get it is we make the f vector the coefficients of the powers of x-1, starting at x-1 to the 0 and going to x-1 to the d+1. If you then expand this out and write it as a polynomial in x, the hi's are defined that way. And if you want, you can solve this equation for hi in terms of fi. And we see that hi is some alternating sum of binomial coefficients times the fj. I wanted to pause briefly to talk a little bit about where this comes from because it seems a little unmotivated. Like a lot of stuff in the study of simplicial complexes, historically, this is kind of the convergence of several different streams of mathematics. This formula comes from the theory of convex polytopes. So if your simplicial complex is the boundary complex of a simplicial polytope, then this quantity shows up in like the late 1800s, early 1900s in what are called the Dane-Somerville equations, which are sort of an almost minimal set of defining equations for the face numbers of the boundaries of polytopes. And they also have some kind of intrinsic meaning in terms of like the angles of a polytope. So Dane and Somerville showed that all boundary complexes of polytopes satisfy some equations involving this complicated alternating sum. And then later on, people just, to save space, just gave these special names. Also, the H's, I think, I have to check, I believe they come from commutative algebra, because this is also related to something called the Hilbert series of a certain commutative ring that we'll talk about later. So if you're a little bit more familiar with that, these are the numerators of the Hilbert function, if you know what that is. And if not, don't worry too much about it. So I believe that this quantity on the bottom was known first, and then they realized that there was a simpler expression for it in terms of these algebraic definitions. And I should say that this really is reversible. Like, you know, written in this way, it's kind of clear that I can reverse and get back the F's from the H's. So the F and the H vector really do have the same information, just encoded differently. So here's our continuing running counterexample. And we can check that the F vector is 1, 5, 6, 2. So it's got one empty face, 5 vertices, 6 edges, and 2 triangles. And I claim that the H vector of this thing is 1, 2, minus 1, 0. And here's the calculation that you do. I just plug these numbers into our formula and expand. And you can double check my arithmetic if you'd like. I have to always double check. And we'll see that we get 1, 2, minus 1, 0 as our H vector. So one thing to notice is that the entries of the F vector are all positive, and the entries of the H vector don't have to be. And this is, in some sense, it means that there's maybe not necessarily an obvious combinatorial interpretation for the entries of the H vector, because, you know, if there's a negative number of something, you can't really count stuff with, there's very rarely a negative number of things. And so more about where this minus 1 is coming from later. And so one last kind of player that I need to introduce is the notion of a relative complex. This is very much like the notion of a relative or a pair of spaces from algebraic topology. So if gamma and delta are simplicial complexes with delta a subset of gamma just as a set system, then the relative complex gamma relative to delta is just the faces of gamma that are not in delta. And relative complexes actually include absolute complexes as a special case, because I can go relative to the empty set and I get back the big complex. And these have a much less clear kind of geometric interpretation. You can sort of draw pictures of them, but it's not so easy anymore. But the face numbers, we can easily define face numbers of a relative complex just by taking the difference of the numbers of I-dimensional faces. And then we have this same polynomial transform, so we can define a relative H vector for this relative complex. And you can check that if gamma and delta both have the same dimension, then actually everything we do works out nicely enough that the relative H vector is just the difference of the H vectors of the big complex and the small complex. So we're going to be working with relative complexes, and in particular with ones where both complexes have the same dimension, so that we really can think of the H vector of this relative thing as a difference. So as I mentioned before, these F and H vectors are equivalent, and Fi really counts something. Always. Like this always has a very easy combinatorial interpretation. It's the number of faces, it's the number of I-dimensional faces of gamma that are not I-dimensional faces of delta. So it's kind of natural to ask, we've got two equivalent integer vectors. One of them counts something. What about the other one? And the answer is sometimes, when the complex is sufficiently nice, we do have very good combinatorial interpretations for these entries of the H vector. And the first of these that we're going to talk about is partitionability. So that's one of the words that I didn't explain from the title. So partitionability is a little bit technical, but it's not too bad. So let P be a finite poset. We said that P is partitionable if we can decompose P into a disjoint union of Boolean intervals, such that the maximum of each of these Boolean intervals is a maximal element of P. And a Boolean interval is just a poset that's isomorphic to the Boolean lattice, which is the set of all subsets of some set. And so here's a picture. So our poset P is in black down here. And partitionability means I can carve up this poset into disjoint Boolean lattices. So here in red, I've got a Boolean, and I need each Boolean lattice to go all the way to the top of my poset. So here in red, I've got a Boolean lattice of length 2. And then I've got 4 more elements left in my poset, these two this sort of N-shaped subposet. And each of these, I break up into just a Boolean lattice of size 1. So this poset down here is partitionable. And we define a relative and hence an absolute complex to be partitionable if its face poset is partitionable. And there's a proposition due to, I believe, Ball and Proven, which says that if gamma relative to delta is a partitionable relative complex, then this HI of the relative complex is the number of Boolean intervals in the partitioning of the face poset whose least element is a face of size I. So we've moved from dimension to size. So over here, if this were the face poset of a relative complex, then this red Boolean interval would contribute 1 to H0 because the bottom element always has size 0, or if this were a pure complex, I should say, an absolute complex. And then this blue one would contribute 1 to H1, and this green one would contribute 1 to H1 because the bottom elements have size 0, then size 1, and then up top is size 2. So if this were the face poset of a simplicial complex, its H vector would be 1, 2, 0. Okay, so that's partitionability. And then non-partitionability is, well, I told you that the bow tie would be a running counterexample. And here is the first property that it doesn't have, partitionability. So you can check for yourself that essentially by symmetry, no matter what I do, I'm never going to be able to partition up its face poset into Boolean intervals. Because I can try, so I have to get the bottom element, and I have to go all the way to the top. So I'm going to have one Boolean interval that's the set of all subsets of 1, 2, 3. And then I have 4, 5, 3, 4, 3, 5, 4, 5, and 3, 4, 5 left. And if I try and partition up, I'm going to run out of facets. So I can go up from 5 to the top. And that's a Boolean interval, that's fine. But now I have 4 and 3, 4 left, and there's no facet above them. So I can't have a Boolean interval that goes all the way to the top that catches 4 and 3, 4. So this is going to be non-partitionable. And by symmetry, you know, this is essentially the only thing you can try for this complex. So it's not going to be partitionable. And I mean, another way to check that is this theorem of Ball and Provin says that the H vector has to be non-negative for any partitionable complex. And we've already seen that this H vector has a negative entry. So it can't be partitioned. So it's kind of natural to ask, well, okay, we have a nice interpretation of the H vector for partitionable complexes. What about non-partitionable complexes? You know, how far is this H vector for a non-partitionable complex away from like actually counting the number of intervals in some partial partitioning, let's say? You know, how far away is this interpretation for like the general case? And it turns out that somewhat surprisingly, the answer is most complexes are pretty close to partitionable complexes in some sense that I'm about to describe. So let's let gamma be a supercomplex of delta. We said that gamma is a partition extender for delta if gamma relative to delta and gamma are both partitionable. And one of the first results that Doolittle, Goeckner, and I came up with is that if you've got a pure d-dimensional complex, then there is always a pure d-dimensional partition extender. And the reason that this is useful for this combinatorial interpretation game is that we can rearrange, because they have the same dimension. Remember that I mentioned that if both complexes are the same dimension, then the H vector of the relative complex is the difference of the H vector of the big complex and the H vector of the little complex. But if we assume that gamma and gamma relative to delta are both partitionable, then HI of gamma relative to delta and HI of gamma both have combinatorial interpretations by the result of Ball and Provin in terms of, you know, counting Boolean intervals whose bottom element has a certain level in the Facebook set. And so rearranging this equation, I get that HI of delta is equal to HI of gamma minus HI of gamma relative to delta. And so HI of delta it measures the difference between a partitioning of the big complex and a partitioning of the relative complex. So how many more, HI of delta is how many more Boolean intervals whose bottom element has size I are there in a partitioning of the big complex than there are in a partitioning of the relative complex. And this actually, so it's maybe not obvious, but this proposition says that because HI is an invariant of HI depends only on the F vector, then any partitioning, these quantities are going to be the same. So really, the existence of partition extender says even if the entries of my H vector are negative, they maybe don't count something, but they're the difference between two things that we know how to count. So it's almost like sort of the second best you can do. We can't necessarily get a direct interpretation, but we got two things and we're measuring how far apart they are. And so I briefly want to sketch how we actually constructed these things. And the way we did it is we had a kind of involved recursive construction, but I can explain sort of what we were aiming for. The idea is rather than try and, you know, partition delta and then maybe get obstructed somehow, and what we're going to do is we're just going to cook up a special complex that can, given any I-dimensional face, kind of partition it away. So we're partitioning everything in the, we're cooking up with like a little auxiliary complex that we can glue onto our complex that allows us to partition every face. And so I won't go through all of the messy technical details, but the idea is we cook up a special complex so that we've got a specified face along which we're going to glue it to the complex we want to partition, so that the relative complexes are partitionable in the correct way. If you're curious, I can talk about the details later. So, you know, if you want to scan this slide, go ahead. But the idea is, again, the main thing I want you to get out of this slide is that we get gamma by the big complex by gluing a bunch of stuff to the complex we actually wanted to try and partition. We glue like a bunch of auxiliary complexes, one for each face. And then
Alex, is the idea here, so it looks like you're sort of greedily trying to partition delta, and then at some point you get stuck because you don't have enough facets, and then you just glue on more facets to fix that up?
Actually, we're being even greedier than that. We're not even trying to partition delta because we actually thought about that, but then we realized we couldn't think of a good way of greedily partitioning and like actually keeping track of what was going on. So we're just like, okay, forget about even trying to partition, just like glue something onto literally every face, including the empty face, that lets us be partitionable both with and without that face, is essentially the idea. So we want to, each of these relative complexes that we're gluing on, we got a special face, and you're partitionable without some facet that contains it, and also if I throw out that facet, but also throw back in the face. So you can check that this actually allows both the big complex with all of its ornamentation glued on, and the relative complex, which just consists of the stuff we glued on without delta underneath it. These are both going to be partitionable by construction. So if people are curious about more of the technical details, I can talk about that at the end. I don't want to get too bogged down into it because it's a kind of a doubly recursive construction, which is kind of not so enlightening unless you see some examples. But does that kind of answer your question, Russ?
Yeah, thank you.
Cool. And so here's a picture of what's going on. So our underlying complex delta in this case is going to be a pair of edges. So this is a one-dimensional complex, also known as a simple graph. You can check that this is not partitionable. Actually, it's not a terribly difficult exercise that a graph is partitionable if and only if it has exactly one connected component that's a tree. So if you decide you're not as interested in the rest of my talk, you can try and work out the details of that argument. It's pretty easy. And so in blue, we now get what our partition extender looks like. So here's what the big complex is. So we started with a pair of edges, and then we throw on a bunch of triangles, a bunch of hollow triangles. And as you can see, this is somewhat bigger than our original complex. And in one sense, it's a very inefficient construction, because you can check that if I just added one edge connecting these two parallel edges, I also get a partition extender, and it's going to be much smaller than this sort of arbitrary one, much smaller than the one we construct in our proof. And just as kind of a rough upper bound for the number of faces we add in our construction, it's going to be more or less doubly exponential. 2 to the d minus k minus 1 plus d. So this is a very, very big construction, but it does always work. And I did want to say one thing in kind of defense of this construction. So remember that hi of delta is the number of intervals in any partitioning of gamma whose bottom element has size I minus the number of intervals in the partitioning of gamma relative to delta whose bottom element has size I. So we can keep track. So every face, by construction, every face of delta kind of contributes a certain number of intervals to the partitioning of gamma and to the partitioning of gamma relative to delta. So if you go through and kind of keep track of what the contribution of each face of delta is to the H vector, we actually just get back this formula for hi of delta. So this kind of gives us a counting witness to this formula that you otherwise get through algebraic means. So that's kind of one nice thing about our construction, is that this falls out quite natural. So there are a lot of questions that kind of naturally arise from this construction, which is, okay, we've got a very non-minimal one. We know in the case of graphs that it's pretty easy to cook up essentially minimal ones, minimal partition extenders, because you can always just, decrease the number of components to 1 or throw in edges to induce cycles in components that are trees. So is there some way that we can construct minimal partition extenders? And there's, maybe a couple of different measures of minimality that you can use, such as the number of faces you add, the size of the relative H vector, or other stuff, maybe a number of facets. We have no idea. Russ's initial idea of doing a greedy partitioning and then just like getting rid of faces when you get stuck would definitely be better in terms of size than what we've done so far, but it's unclear how small you can really get in general. And another natural question is, if you have a minimal construction with respect to size, is it unique in any sense? In the graph case, it's certainly not absolutely unique, because there's 1, 2, 3, 4 possible edges I could add. So it's not completely unique, but I mean, the relative complexes in all such cases are going to be combinatorially isomorphic, which is to say they'll have the same face poset. So maybe you can show that, all minimal ones have the same face poset or something. It's unclear. We've thought about it some, but haven't made much headway. Another kind of question we can ask is, if I fix delta, what can we say about the set of H vectors of the relative complexes that we get, where the big complex is a partition extender? It's not even clear to me that it's going to be a cone. I suspect it is, but I haven't been able to prove it. I think you can say that like this set contains the all zeros vector if and only if delta is partitionable. But just the structure of the set as like a subset of z to the d, d plus 2, I guess, is pretty mysterious at the moment. Okay, so any other questions about kind of this construction here? So one other thing we can do is we can extend our construction to the non-pure case with a little bit of extra effort. So a complex is non-pure if we've got maximal faces of different dimensions. So you can think of like a solid triangle with an edge coming off is sort of the prototypical non-pure complex. So with a little bit of extra care, not too much, we can construct a non-pure partition extender. So that's a non-pure complex gamma with the same set of facet dimensions as delta. And again, gamma and gamma relative to delta are non-pure partitionable. And if you're familiar at all with the sort of combinatorics and topology of non-pure complexes, the correct analog of the H vector is what's called the H triangle, which is due, I believe, to Bjorner and Wax, if I'm remembering right. And it's a two-dimensional array that specializes to the H vector in the case where the complex is pure. But then it has the same kind of difference property for relative complexes. And so we can, again, view the H triangle of an arbitrary complexes in the same way a difference of H triangles of partitionable relative complexes. And in the non-pure case, there's again, the entries of the H triangle count certain of the Boolean intervals in a partition by the size of the bottom and the size of the top, essentially. Okay, so that kind of is it for partitionability. And I mentioned one other term in the title of this talk, which is Cohen-Macaulayness. So I'm going to talk about that now. Cohen-Macaulayness is an algebraic property that can also be translated into topological, but it comes from commutative algebra. So one of the nice things about the combinatorics of simplicial complexes is that a simplicial complex is essentially equivalent to a certain class of graded K algebra. So there's a one-to-one dictionary between the topology and combinatorics and commutative algebra. And the commutative algebra side has been very well studied historically. So this lets us move a lot of problems back and forth. So if delta is a simplicial complex and we fix the vertex set to be the integers 1 through n, so bracket n, this notation just means the set 1 through n. And we'll let boldface K be a field or Z. Then the Stanley-Reasoner ring, or the face ring, is defined to be the following quotient. So K of delta is the polynomial ring in variables x1 through xn modulo a certain ideal called I of delta. And I of delta is the ideal generated by the non-faces. So it's generated by all monomials of the form xi1 through xim, where the set I1 through im is not an element of delta. So we basically kill all monomials that are whose indices are not a face. And this is there's been a lot of very cool combinatorics that has come from studying these face rings. They were instrumental in Stanley's proof of the upper bound theorem and have been actively studied since the 70s. So there's two of the many important ring theoretic invariants of this object are depth and Kroll dimension. And I'm not going to go into too much detail about what these are, but I will just say that they can both be defined purely in terms of the simplicial complex via our dictionary. It's a general fact from ring theory that depth is always bounded above by dimension. And if they're equal, then we say that K of delta and therefore by translation delta are said to be Cohen-Macaulay over K. And Cohen-Macaulay algebras, there are, multiple books just on studying these kinds of rings. So they're a very deep subject. But I can kind of explain sort of briefly what the idea is. So K of delta is Cohen-Macaulay if and only if it has a certain kind of polynomial basis, essentially. Cohen-Macaulay means it has what's called a regular homogeneous system of parameters, which is theta 1 through theta d, which are homogeneous and algebraically independent. So they're not the common roots of any polynomial. And there's a set eta 1 through eta s of homogeneous elements of K of delta, which, for which every f can be written uniquely as some sum eta I times a polynomial in the thetas. So these thetas are some kind of like a polynomial basis for K of delta. And each pi depends on f. And moreover, if we quotient K of delta by the ideal generated by these theta 1 through theta d, we get a finite dimensional graded vector space over K. And you can work through a bunch of commutative algebra, but what winds up happening is that our H vector is actually the rank of the graded pieces that we get when we do this quotient. So in the Cohen-Macaulay case, if you go through and translate all the commutative algebra back to combinatorics, we actually do have a combinatorial interpretation again of the H vector for these kinds of complexes, and they're the dimension of some vector space. Okay, and so now I've talked a lot about the algebra, and I want to go into sort of the combinatorics and topology of what this Cohen-Macaulay condition is. And to do that, we need the notion of a link. So the link in delta of sigma is how this should be read. That's the set of all tau in sigma such that tau union sigma is a face, but tau intersect sigma is empty. And the picture you should have is that this is a combinatorial notion of like the punctured neighborhood around sigma in delta. So I guess spoilers, the bow tie is also not Cohen-Macaulay, but if you look, so here's our bow tie complex delta. The link in delta of the vertex 3 is the set of all faces whose union with 3 is another face, but that don't intersect 3. So 3, 4, 5 is a face, and 4, 5 does not contain 3. So we got 4, 5 is in the link. And similarly, 1, 2, 3 is a face, and 1, 2 does not contain 3. So the edge 1, 2 is in the link. And if you look, you can kind of imagine I intersected this complex with a circle, and then with a punctured circle around 3, and then this kind of deformation retracts onto 1, 2, and 4, 5. So the link is really like, what does 3 see if you're standing at it in the complex? So in terms of links, there's a famous theorem of Reisner, which gives a complete characterization of Cohen-Macaulay complexes. So a complex is Cohen-Macaulay over K if and only if you look at the reduced simplicial homology groups of the link of every face, including the empty face, the topology, the homology vanishes except maybe at top dimension. And here top dimension means it should be the dimension of delta minus the dimension of sigma minus 1. And then there's a similar notion of relatively Cohen-Macaulay. And a relative complex is relatively Cohen-Macaulay if you take the quotient module of the ideals of non-faces, and there's a notion of Cohen-Macaulay modules from commutative algebra. But it's a theorem of Stanley that, again, this can be translated into some kind of homology condition on the links. So here, you're relatively Cohen-Macaulay if the links, the homology of the relative homology of the link of sigma and gamma and the link of sigma and delta vanishes, except maybe at some kind of top dimension. So as I said, this bow tie complex is not Cohen-Macaulay. And here's why. So here's the link of 3 is this pair of edges. And we can look at the reduced zeroth homology over any field. The reduced zeroth homology is the number of components minus 1. So in this case, or it's k to the number of components minus 1. So in this case, the reduced zeroth homology is k. But we want this homology to vanish because the dimension of delta minus the dimension of the vertex 3 is 2 minus 0, and then minus 1. So I got 1, which means that my only non-vanishing homology should be in rank 1 instead of rank 0. So this fails this link condition, and so we're not going to be Cohen-Macaulay. And so really kind of the obstruction is this vertex here. So there's something that locally goes wrong at this vertex, and that's what's preventing this complex from being Cohen-Macaulay. And so since we were able to cook up something for partitionability, our next trick we decided was to see if we could cook up some kind of super complex that lets us build out to Cohen-Macaulayness. So we say if delta is d-dimensional, we let gamma be a super complex of delta, and we let it also be d-dimensional. We say that gamma is a Cohen-Macaulay extender for delta if gamma and gamma relative to delta are both Cohen-Macaulay. So if they both satisfy these homology conditions on links. And by contrast to the partitionable case, there's a lot of complexes that don't admit any such kind of extender. So delta has a Cohen-Macaulay extender if and only if the depth of k of delta is greater than or equal to the dimension of k of delta minus 1. So remember that depth is always less than or equal to dimension, but so it turns out you only have one of these extenders if your depth is not too low. So if depth equals dimension, then it's Cohen-Macaulay already, and we don't have to worry about that. So the lowest the depth can be is dimension minus 1. But then if the dimension is within this range, the depth is within this range, you have a Cohen-Macaulay extender. And in fact, anything you pick is always guaranteed to work. So if depth falls within this range, then if you pick any d-dimensional Cohen-Macaulay complex that contains delta, then it's always going to be a Cohen-Macaulay extender. So it's kind of a funny contrast to partitionability. In the partitionable case, any complex you can think of has at least one partition extender, but you kind of have to work at it. You need to actually build it up. In the Cohen-Macaulay case, a lot of complexes don't have a Cohen-Macaulay extender, but if you have one, anything you try is going to work. And the proof of this is entirely in homological algebra. You use like the Meyer-Vietoris sequence and the long exact sequence of the pair of links, and you can translate depth is greater than or equal to c into some kind of link condition, and you just go through and you check a lot of homological algebra type arguments, and you can show all of this. And so in particular, I can just take the complete d-dimensional complex on if delta has depth equal to dimension minus 1, I can just let gamma be the complete complex on however many vertices delta has, because that's Cohen-Macaulay. And then that's always going to be a Cohen-Macaulay extender. So I don't even have to add any vertices. I can always just add a bunch of facets, essentially, and I'll be able to get to Cohen-Macaulayness in a relatively Cohen-Macaulay way. Okay, so that's the results that we currently have. And I want to talk in the last couple of minutes about what some potential future directions are and why we started thinking about this stuff. So if you work in this sort of side of algebraic and topological combinatorics at all, if we talk about partitionability and Cohen-Macaulayness, your thought probably naturally goes next to shellability. So we call a relative complex shellable if there's a total ordering of the facets of gamma relative to delta, f1 through fm, so that fi plus 1 relative, the complex generated by fi plus 1 relative to the complex generated by the first I and delta has a unique minimal face for all I. So here's an example of a shelling of an absolute complex. So I need a total ordering of the facets of this complex such that every time I add a new facet, I have a unique minimal new face. So I start at F1. There's a minimal new face I've added, which is the empty set. I can then throw on F2, and you can see that the minimal new face that I added was actually the vertex 6. If I add F3 to the complex generated by F1 and F2, there's a minimal new vertex 2, and so on. So if I add F4 to F1, F2, F3, 7 is a unique minimal new face. And then finally, when I add F5, 1 is a unique minimal new face. So this is a shellable complex. And shellable complexes are nice. The notion originated again in the theory of polytopes. They kind of let you do induction on complexes. They say that your complex has been built up in a sufficiently nice way. And so it's kind of natural to ask, can we cook up some notion of a shelling extender? So that would be a pure d-dimensional complex gamma containing delta such that gamma and gamma relative to delta are both shellable. So these shelling extenders can't always exist. And we know this because a pure shellable relative complex is partitionable and relatively Cohen-Macaulay. So we need at least for delta to admit a Cohen-Macaulay extender. And our conjecture is that if delta has a Cohen-Macaulay extender, so if depth of delta is greater than or equal to dimension minus 1 for all k, then delta has a shelling extender. This is our conjecture because literally every time we've tried, it's worked, but we have no idea how to actually go about proving this. And one reason we care about shelling extenders is a pretty famous conjecture of Simon famous within this sort of subfield. So let delta be a pure complex. We say that delta is extendably shellable if any partial shelling order of the facets can be extended to a full shelling order. And in 1994, Simon conjectured that the D skeleton of the N simplex is extendably shellable for all N and D. And it's still a conjecture, and we've got a lot of partial results. Many partial results are known, but nobody's been able to prove it, and it's not even clear how many people believe that it's true. So some cases are trivial. So if the D is less than or equal to 1 or greater than or equal to N minus 1, it's very easy to check. The case D equals 2 was proved by Bjorner and Eriksson in 1994 when they were studying matroid complexes. D equals N minus 2 was proved quite recently by Doctorman and also by Bigdeli, Yazdanpour, and Zarnahandi. And then the most recent progress on this is actually from this year. Doctorman and I think some REU students put out recently a short paper that's pretty cool. It's worth checking out if anything in this talk has interested you. So if the initial sequence of your Schelling order has a slightly stronger property called vertex decomposability, then you can't get stuck. This is one of the main things they were able to prove, and it's some very nice arguments, so it's worth checking out their paper. It's up on the archive. So if your initial segment of the Schelling order gives you a complex that's vertex decomposable, you can always extend it to the D skeleton of the n simplex. So I just want to say, you know, are studying this these Cohen-Macaulay extenders, we noticed that if the depth, if a Cohen-Macaulay extender exists, we can always find a Cohen-Macaulay extender without adding new vertices. And if we could further find a Schelling extender without adding any new vertices, this would actually give us a proof of Simon's conjecture, because we could always keep going. And so the last question that we have is, suppose that delta admits a Schelling extender, which we don't even know is the case. Can we do it without adding new vertices? And that's all I have to say today. So thank you very much for listening.
Thank you, Alexander, for the very nice talk. So it's time for questions, suggestions.
Is there a nice topological description of this partition extender?
Not that I know of. We did it purely combinatorially. I mean, it's like I said, in all basically the idea is you want to add a lot of cycles of sufficiently high dimension, because things that kind of look like annuli are partitionable because you can match stuff up. But I don't know that there is, and I mean, they can be pretty wild objects in general. So I think it might be easier to focus on, like, if you've got smaller ones, maybe there's a nice thing you can do. But that's a good question. It's we kind of followed our noses and it worked, and you know, we haven't been able to figure out a nicer description of them yet.
It reminds me a little of this stuff from Stanley and from Duval showing, giving matching in the face lattice of the acyclic complex.
Oh yeah, the decomposition thing.
Yeah.
Right. Yeah.
I'll mention, but by the way, there's a sensible, greedy way of trying to partition. I mean, I don't know if it helps very much, but well, if you want to make it canonical, then order everything so that you always have the least thing to choose. Mm-hmm. So now match the empty set to the least thing available. Go through the unmatched vertices one by one, match them to the least things available. Right. Go. So if you do that on your small example, you get a slightly smaller partition extender. I think you get, well, you get the one edge is left alone, and then you attach a gadget to the other edge to fix up the one vertex.
Right. Yeah, and then you don't have to throw on that thing, the big thing at the bottom for the empty set.
Yeah.
Yeah.
So with the Cohen-Macaulay extender, do I have it right that the idea is, let's see, so the reason that you can't do this if the depth is too low, but the depth tells you what dimension you can have holes in topological or really homological sense. So is the idea that to fill in, you're adding I+1 faces, And with an I+1 face, you can only fill in an I whole.
I think the idea is there's this notion you can depth greater than or equal to C says that the links of all, all faces of certain dimension have the vanishing homology property. And then, so then you just use the depth lemma, which is that, if you've got a short exact sequence, the depth can't change too much. And you look at the long exact sequence for relative homology. And then the non-existence just says, if my depth is too low, there's going to be some face where I'm forced to introduce homology or relative homology in a place where there shouldn't be. So maybe topologically your intuition is right, but our argument was much more sort of straightforward homological. It's like it just can't work because of the way the long exact sequence goes.
Have you tried looking at bad examples and for counterexamples for the?
Oh, sorry, you cut off for a second.
Yeah. Have you tried? There are these bad examples in dimension 3 of non-shellable balls.
Mm-hmm.
Have you tried to look at them? I mean,
not really, no, but that's a good point. I know there's like the Hachimori has like his bestiary of like counterexamples that might, and they're all like implemented in Sage and stuff, so it might be worth taking a look at.
Usually with shellings, if some general statement like that is not obviously true, then it's then there's a counterexample.
Yeah.
But I don't see how to find it right away except to play.
Yeah.
Okay. Any other question? Well, if not, then thank you, Alexander, once again for the talk, and really I hope that
thank you.
You will be able to visit Cooper sometimes also in live in the in the future. Hope soon.
Yeah, thank you.
It's a lovely place. We're on the seaside, and it's much warmer than Sweden.
Yeah, it hasn't been so cold so far, but